Imagine being able to take a picture of an object and have a computer recognize what it is. Wouldn't that be crazy? But it turns out that you're probably using image recognition even if you don't know it. It's the technology behind Google Lens, where you can point your camera at an object and Google will tell you what it is and give you more information about it. And it's behind Apple's FaceID, which allows you to unlock your iPhone by just looking at it. In the future, it'll also allow cars to drive by themselves because with image recognition, they can now understand the world around them. This is the sort of stuff that people would have thought impossible 15 years ago, but now it's here and available almost for free. So the underlying technology behind this is a special type of deep neural network called a convolutional neural network. Convolutional neural networks, or CNNs, are used by most state-of-the-art systems today. So before CNNs, a popular approach to image recognition was using kernels. So kernels are just matrices of numbers. They can be 3 by 3, 5 by 5, so on. And they're placed on top of a segment of an image. So the pixel values of the image are multiplied by the numbers in the kernel, and then all of those numbers are added up together, and that creates the first part of another matrix. Then the kernel slides over, does the same thing, and that makes the second number in the new matrix. So once this kernel has scanned over the entire image, it outputs another matrix. So the point of these kernels is to extract certain features from an image. For example, this kernel outputs a high absolute value whenever it detects a horizontal line. We can also have multiple kernels. For example, one might detect vertical lines, another might detect horizontal lines. And then when we scan both of these kernels across the image, we end up with another image that has 2 channels instead of 1. So let's say our image doesn't just have 1 channel, so it isn't grayscale, but it has 3 channels for each color RGB. So then rather than having a 3 by 3 by 1 dimensional kernel, we'll have a 3 by 3 by 3 dimensional kernel. And we'll do the exact same thing we did with a grayscale image. So the numbers in the kernel are multiplied by the numbers in the image, and the resulting numbers are added together, and then that creates the first number in a new matrix. And of course, we can have multiple such kernels, so then we output an image with multiple channels. So basically what deep learning does is take this a step further. So instead of having all of the weights of the kernels fixed, these weights are now trainable using deep learning approaches like gradient descent. We can also have multiple layers of these kernels which feed into each other. So for example, the output of the first layer would be the input to the second layer. And in this way, we can extract more abstract features. So for example, the first couple layers, they might detect lines. And then the next couple layers would detect shapes. And the final layers would extract higher level features. So things like faces or objects. Then the output of the last convolutional layer is flattened and then passed through a couple dense layers. Finally, the data is passed through a softmax of however many classes you have. So normally in deep learning, sigmoid or tanh are the more popular activation functions. But for convolutional neural networks, ReLU is actually preferred because of a couple reasons. First of all, it's less computationally intensive to calculate because you literally just take the maximum between 0 or the value that you gave it. And secondly, it's less susceptible to the vanishing gradient problem. Another layer you'll often see used in CNNs are pooling layers. So the most popular used right now is max pooling. Basically what it does is it takes a region of an image and takes the maximum of that, right? So whichever pixel value is the highest. So because our images these days are very high resolution, we don't want to deal with that much information, right? We want to make our network as simple as possible so it trains quickly and requires less computation power. And max pooling is able to summarize those local areas to basically compress the image. There's also a lot of newer techniques that you can use to make these systems more accurate and have them train faster. Because of them, the error rate on the annual ImageNet challenge has dropped from 25% down to lower than 5%, which is actually better than what a human could do. You can read about all of these other techniques and some finer details of neural networks in my article down in the description below.